All right, we're going to get started on section 9.2. This is a long section, so we're going to divide it into two parts. So the title of this section is the Legendre Symbol and its properties. Legendre Symbol is actually a tool that we use to determine whether a certain integer is a quadratic residue of actually an odd prime. All right. So we're going to start with defining the Legendre symbol and prove some of its properties. Then we're going to follow this with some examples of evaluating Legendre symbols using its properties. Then we're going to state the two fundamental problems in the quadratic residue theory. What is, we are interested in when we're talking about the quadratic residues. Remember, a quadratic residue is an integer that is a solution for simple quadratic equation. X squared is congruent to a mod n. All right, where n is an integer bigger than 1. Then we're going to look at some of the applications of Legendre symbol. Among the applications, we're going to show that there are infinitely, for example, many primes of the form 4k plus 1. Then we're going to introduce Gauss's lemma as actually a practical tool to evaluate Legendre symbol. In other words, evaluating Legendre symbol, it turns out, using the properties, is okay for small primes, but when the prime gets bigger, larger, then Gauss's lemma actually is a better tool. In the second part of this lecture, we're going to introduce another version of actually Gauss's lemma that makes even the evaluation of Legendre symbol even simpler than the original Gauss's lemma. Then we're going to also, in the second part, talk about little more applications of Legendre symbol. So this is what we hope to accomplish in this lecture. So we're going to start with the definition of Legendre symbol, and as I said, Legendre symbol is an indicator, sort of, whether a certain integer is a quadratic residue for an odd prime or a quadratic non-residue. All right? So keep that in mind as we put the definition. So it's a notation that it turns out to be very simple, however, it's very effective notation for many of the things that we're going to be doing in this section as well as in the next two sections. All right, so here's the definition. So let B be an odd prime and A an integer, positive, negative. Of course, we don't want it to be 0 because that's a trigger. An integer, relatively prime. To the Legendre symbol denoted by this symbol, we need parentheses, then A slash P. This is not division, it is just a notation. All right? It's denoted by this and defined by this rule. In fact, it's actually, you could think of it as a function, all right? It's an arithmetic or a number theoretic function by this. So this is equal 1 if A is a quadratic residue of P. Remember, this is equivalent means that x squared congruent to P has solution. Of course, integral solution. Always we are interested in integral solution, solutions that are integers. And -1 if A is a quadratic non-residue. Of B. Means x squared congruent to A mod B has no solution. All right, so this is what Legendre symbol is. Other notation for Legendre symbol, and sometimes I may slip and write it as A like this. All right, or some authors write A, B like this. Also, some authors actually define the Legendre symbol to be 0. 0 if B divides A, or means greatest common divisor of A and P is bigger than 1. All right, whenever these are not relatively prime, we, some authors actually use this value for the Legendre symbol. So this way, we actually can, this becomes totally number finite function is defined for all integers A, not necessarily just, relatively prime. So this is one of the advantages. For us, it's not going to be, a big deal. All right. So let's look at an example. We've seen quadratic residues for the prime 13. All right, we actually did look at example, we listed all of them. For example, you take P equal 13. P equal 13. Its quadratic residues are these integers 1, 3, 4, 9, 10, and 12. As you see, these are not squares. Not all of them are squares, all right? So they are squares mod 13, basically. That's really what it is. And the quadratic non-residues are the other integers, which is 2, 5, 6, 7, 8, and 11. And as you see, we have half of those are quadratic residues, the other half is quadratic non-residue. So what the Legendre symbol is saying that if you take, for example, 10 by 13, this is equal positive 1, as well as this is true for any one of these. When you take Legendre symbol value of these by 13, we call it 10 by 13 in here. And for the non-quadratic residues, we have, let me see if I listed them correctly in here. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. So if I take in here quadratic non-residue, I don't know, 8 by 13 is the same as 6 by 13, and this is equal -1. So as I said, it's an indicator. It is just a flag there, flags out if an integer is, quadratic residue or quadratic non-residue. All right. So next we're gonna look at some of the properties of Legendre Symbol, which translate, the language of quadratic residues and non-residues into manipulation or in terms of this symbol. All right, so this is the first theorem. Theorem 9.2. Again, we're going to let P be an order prime. And A and B are integers relatively prime to P. But not necessarily with respect to each other, okay? Just both of them are relatively prime to P. Then we have the following properties holds. First one, if A happens to be congruent to B mod B, then the Legendre symbol for both of these are equal to each other. And then, in fact, we didn't prove this. We proved that if A is congruent to B, then A is a quadratic residue, then actually B is a quadratic residue, and vice versa. So really, this is what it translates to in terms of Legendre symbol. All right, B, the Legendre symbol for the square of any integer is equal 1. All right. Now you're going to see this is very, very actually straightforward. 3. This is sometimes we call it Euler's criterion. In terms of Legendre symbol. Remember that Euler's criterion is a criterion that determines whether an integer is, again, a quadratic residue or non-residue by taking a to the power p minus 1 over 2. And if this is congruent to 1, then it is quadratic residue. If it is congruent to negative 1, it's a quadratic non-residue. So when we want to put this in terms of Legendre symbol, it says simply this is A by P mod P. So in other words, the evaluation of the Legendre, the Legendre symbol is the same as actually finding or applying sort of Euler's criterion. All right, let's move on and more properties. And B is, I think we're going to look at the product rule. A, B by B is A by B and B by in fact, what this indicates that the Legendre symbol as an number function is completely, all right, the Legendre symbol. So now we put like this is completely multiplicative. E is concerning this A B squared. This is the same as A B. So in other words, Legendre symbol is invariant if it has one, you know, in the numerator, so that, well, this is the numerator, a square. Okay, it would be the same as without the square. The last one, it gives us actually some sort of a formula in general for any prime. 1, b is equal to 1, and we have -1 by p is equal -1 to the p minus 1 over 2. And we can say a little more. In particular, we have, this is this formula for the Legendre symbol for -1. In particular, we have -1 by p is equal to 1. 1 if p is congruent to 1 mod 4. And -1 if p is a prime, of course, congruent to 3 mod 4. All right. We're going to go through the proof of, probably the first one, we already proved that, so I'm probably going to skip the proof of that. That's very, very straightforward. Let's go and actually prove the second property. That is the Legendre symbol for a squared by b is equal almost to 1. Okay? So here's the proof. So a squared b is equal almost 1. So let's consider this equation. The congruence equation x squared congruent to a squared mod. All right. Now, since a b is equal to 1, this implies also a squared is actually relatively prime to p. And this implies that x equal a is a solution to x squared congruent to a mod. All right. So this is and this implies. Sorry, this is x equal a is actually a solution for this. So when you substitute for x by, let me see here, we're going to say that. Yeah, so x equal a is a solution to this, and this implies a solution to this, okay? And this implies that a squared b is equal to 1. Now we're going to reprove this one using the multiplicative property of Legendre symbol. But this is very, very straightforward, actually, the proof here. All right, let's look at C, where we're going to do the Euler criterion. All right. Express Euler criterion in terms of Legendre symbol, basically. So as you know that we have shown this. This is theorem 9.1. and it's corollary. Okay, that if A is a quadratic residue of P, then A to the P minus 1 over 2 is congruent to 1 mod P. And if A, actually this one if and only if, okay? A is a quadratic residue for P if and only if. And A is a quadratic non-residue of P if and only if A P minus 1 over 2 is congruent to negative 1 mod P. Now, in terms of what is this is equivalent to? So this is equivalent to saying that A by P, all right, is actually let me see how I'm going to say this one. A over P is congruent to the A P minus 1 over 2 mod P. Well, because all we get for, since we have, this is congruent to this, and the same quantity is congruent to negative 1, then we have A to the P, they are congruent to each other, mod P, and then the Legendre symbol is going to be congruent to this. Let me actually make sure that I'm doing this correctly. All right. Yes, since we have all right, let me actually add something before I make this statement in here, just to make it more clear. So we also have, by definition, A is a quadratic residue of P if and only if A over P is equal to or congruent to is equal to 1, all right? And A is a quadratic non-residue if and only if A by P is equal to 1. So in other words, then we have A by P is going to be congruent to same thing, P minus 1 over 2 mod P. Because whenever the right hand side give me 1, This one will be 1, all right? And when the right hand side is congruent to -1, this will be also -1. All right, now let's move on to part D, all right? It's really just a restatement, just need to make sure that you got the correct reasoning. All right, so D, need to show, remember, that A, B, P is equal A, B, B, P. All right, let's look at this by part C, that is the Euler's criterion. This one is congruent to A, B. Now remember that if A is relatively prime to P, and B is relatively prime to B, then their product is relatively prime. And then we have this one by part C mod P. This is by part C. And now we also can write this as equal, actually, or we could make it congruent to mod P. And this of course is congruent to A, again by the same thing, by P, and then B by P, again mod P. Well, that's not enough, because here we're saying it's congruent. Here I want to show it is an equality between the the Legendre symbol. Now we need one other thing, that we know that we have this A, B by P is equal plus or minus 1, all right? And the product, in other words, the two sides of the congruence, this is also equal plus minus 1. It depends, of course. Now the question is, can they be different? Okay, I claim no, they cannot be different. So this is what I'm going to show. So I claim that A, B, I, P is in fact equal to this. Well, let's assume by contradiction. So this implies one side is going to be positive 1 and the other side is going to be negative 1. By symmetry, it doesn't make any difference. So we may assume that they are not equal. Assume that by assuming left-hand side is equal, let's say 1, and right-hand side equal negative 1. Well, we know from what we have proven, but we had shown about that 1, which is the left-hand side, is congruent to negative 1 mod P. Well, this implies that P is is going to divide 2. But this is a contradiction since P is an odd prime. So in other words, this assumption, assuming that these are not equal, is invalid. So they must equal to each other. So therefore, A P by P must be the same. They are not just congruent, actually to each other, but they are equal, all right, to each other. All right. Now this provides another proof for the second property. It follows from this statement very clearly, of course. So let me put it in. So here's another proof. A squared P is always equal 1. I know that A by P is equal plus minus 1. All right? Then we have A P is equal squared. All right? This is equal to A and A. And this one is equal to this is plus minus 1 multiplied by plus minus 1, and always we're going to get plus 1, regardless of what the value of the A by. All right, now the next property also very, very key, which is A squared P by P. Again, everything about relatively prime. A squared P, P is actually relatively prime to P because both of these are relatively prime. So this is again is equal to my previous property, but the first one is 1 times G by and actually I have it A B squared. I think this is the way I stated it. So this is equal the again different, but I think this is the way it's written. All right, one more quick property. The 1 P which is this. This is I can write it as 1 squared, and we saw this is always equal 1. How about negative 1? This one is congruent to negative 1 to P minus 1 over 2 mod P. All right. And this is actually what it is. Now we're going to do the moreover, okay? Now if P is a prime of this form, then this negative 1 to the P minus 1 over 2 is going to be 4K P minus 1, so 1 cancel out over 2, so this is equal 2K, and this is always positive 1. And if P equal 4K plus 3, this implies minus 1 over P minus 1 over 2 is equal to negative 1, and that's going to be 4K plus 2 over 2, subtract 1, and this becomes minus 1, 2k plus 1. So negative 1 to the naught power is equal to negative 1. For the same reasoning, so this implies that we have negative 1 by p is congruent to actually what we say is, let me see how we're gonna write this one. Yeah, so this becomes actually equal to 1 if p is of this form, and negative 1 if p is 4k plus. All right, because actually these are what they are. They should be equal to, because it cannot be just congruent to the negative 1, because they have the same reasoning as I did before. They must actually equal, not just being congruent. All right, next let's look at, exactly what does this say, this f, put it in the table of remark. As I said, all these Legendre symbol is as an indicator to indicate whether a certain integer is a quadratic residue or not. There's the remark. So property E, or F, last one. F can be restated as this. 1 e is equal 1 is equivalent to saying that x squared congruent to 1 mod e has a solution. Quadratic residue. And in fact, we can do a little more. In fact, x sub 0 equal positive 1. And we call it, this is x1. And x2, in general, p minus 1. All right, is also a solution. Is the second incongruent solution. And also notice that x2 is actually congruent to negative 1 mod p. You want to reduce the x2 to mod p, then it becomes negative 1, which we know that, of course, it satisfies this congruence equation. The other one equal minus 1 to the power p minus 1 over 2, and it's written in terms, of course, the number p is of the form 4k plus 1 or 4k plus 3. So this is equivalent to saying that x squared congruent to negative 1 mod p has solution if and only if p is of the form 4k plus 1 and has no solution if and only if p is 4k plus 3. So this is the kind of thing we are looking for using the Legendre symbol, is to translate, quadratic congruences, they are on, general quadratic congruences, to, whether it has a solution or not in terms of Legendre symbol. All right? Which we already, of course, kind of indicated this. So, for example, for this particular remark, if we look at this, So in particular, numerical example, for p equal 13, we have x squared mod 13 as a solution, since 13 is equal 4 times 3 plus 1. Okay, and in fact, the solution in this case, x1 is equal to 8, and x2 is equal to 13 minus 8, which is 5, are solutions. However, for p equal 9p, x squared congruent to negative 1 mod 19 has no solutions. Because 19 is a prime, which is of the form 4 multiplied by 4 plus 3. So it is of the form 4k plus 3. All right? No integer from 1 to 19 actually satisfy this congruence relation. All right, or equation. All right, let's see how we can evaluate a couple of examples of evaluating Legendre Symbol. Using the properties. Of course, you always can use Euler's criterion, but we're going to see that it's not practical when actually the prime p becomes very big. All right, so here's a couple of examples. First one, we're going to calculate the non-simple 10 by 7. All right, by the third property or fourth property, this one is equal to 17 and 5. 17. Of course, we can again use directly the Euler's criterion, to evaluate this, or brute force by trying to find the solution of x squared congruent to 10 mod 17. But at least we know that we could reduce this work this way. And now we can, find each one of these. For example, 2, 17 is congruent to minus 1. B minus 1 over 2, which is 17 minus 1 over 2. So this is plus 1 to the 8. And again, this is congruent to, 2, not this is 2, not negative 1, 2. Mod 17. And by fast exponentiation, of course, this is not very hard to see that this is actually congruent to 1 mod 7. Okay, so you do 2 squared, then 2 to the 4th, then 2 to the 8th, and always reduce mod 17, you're going to find this is 1. On the other hand, the same thing with 5. 17 is equal to 5 to the power 8. And this is congruent to, again, by the calculations, you're going to find this one is congruent to negative 1. Mod 17. Now, when you multiply this actually becomes equal to negative 1. All right? So this becomes equal negative 1. Means, again, this implies that n is a quadratic non-residue of 70. So the equation x squared congruent to 10 mod 17 has no solution. All right? But let's look at another example. Start if you take a negative. Remember that A is any integer, so it could be positive, negative, 31. And again, we can write this as negative 1 by 31, just the negative by itself. And the prime factorization of 42 is 2, 3, and 7. And by calculating each one of these, we know that this one, it is actually congruent to 31, it's congruent to 3 mod 4. So this is going to give you negative 1, 2 over 32. Actually, we're going to find the general formula for 2 by 32, meaning which are, which primes, basically they gonna make the 2 by that prime is positive 1 or negative 1. And actually we're gonna be stating these two theorems shortly here. And now this one is gonna be a positive 1. The 3 is gonna give you negative 1, and the 7 give you positive 1. So altogether give you 1. So this means that x squared congruent minus 42 mod 31 has 2 solutions. Exactly 2 incongruent solutions. 2 incongruent solutions. Of course, then finding this solution, we will learn even a little more later on how to find the solution of these. We already have done this. Again, by trial and error, you could actually do this. So in general, to evaluate a Legendre symbol for any integer, okay, n, we have the following. Actually, just I want to write it as a remark, all right? And yes, it consists of 2 parts. If or let P be an odd prime, and M, it is a product of some other numbers, Mi, I equal 1 up to R, where greatest common divisor of these M sub I and P is equal to 1. These are relative primes. It must be actually primes themselves for every I. Then the MIP, not very hard to see this, is going to be this. And 2, in particular, if M is equal, I equal 1 to R pi alpha I is the prime factorization of M such that P does not equal to any of these PIs. So they become relatively prime. Then the Legendre symbol is nothing but the product PI over P, and we're going to square this, or take it actually to the power alpha I. All right? Actually, it could be in practice, it's going to be easier because if we have any of these primes, okay, it has an even exponent, then actually we reduce it to 1. All right? But in general, we have it this way. All right. Now, I want to state the two fundamental actually questions, all right, or problems in the quadratic residue theory, all right, that we're going to be shooting to solve. Actually, we already solved one of them. Yeah, we're going to be looking to solve the second problem in the next the next section, actually. All right, here, so the two fundamental, or the two fundamental problems of quadratic residue theory. Okay. The first one is this: given a prime P and R prime. Again, we only consider R prime because the only even prime 2, everything is trivial with respect to that when it comes to solving equation x squared mod 2. Okay, so we don't mention it in here. So given an R prime P and an integer A relatively prime to P, then the first problem is then is a quadratic residue of P or a quadratic residue, non-residue, quadratic non-residue of. Right, and remember that this solving these is equivalent to saying is A by P equal 1 or equal -1. And in a sense, we have a solution for this. So the solution for this is this. We have that A by P is congruent to A P minus 1 over 2 mod P. So by evaluating the this power, exponent mod p. If it is 1 or -1, then we have the answer. The only problem with this is this is not practical to calculate a to the power p minus 1 for large values of p. So this is not practical to evaluate for large primes. Even with fast exponentiation, because if p is very large, then reducing is not actually going to be possible, means we still have a very large prime. All right? Later on, as I mentioned, we're going to introduce Gauss's lemma, which make actually evaluating this a little easier. We're going to actually have a couple of lemmas that will make evaluating this a little easier. And even more in the next section, that's the quadratic reciprocity, law is going to allow us even to do better, okay, and being able to evaluate the Legendre symbol. Basically, we don't have to attack or use the this power residue, okay, or exponents in here, then it becomes easier. The second problem is actually much harder than this, and this is going to be our objective in the next section. And actually some of it we're going to start working on even in this section, but the main result is going to be proved using the quadratic reciprocity. So this is the second question, the second fundamental problem. Given an integer a, all right, we need to find all primes, relatively prime, to a, that are quadratic, so that A is a quadratic residue. Okay, so you're going to find all primes to A that A is a quadratic residue for P, and the primes that A is a quadratic non-residue of or for P. This second problem is much harder. Actually, it took half a century to actually come up with a solution. And big minds actually worked on this, Euler, Legendre, and finally the solution was arrived by Gauss. In fact, Gauss, it took him, he actually proposed this when he was 18 years old, and it took him 1 year to actually be able to solve this problem. This is again the subject of the quadratic reciprocity law. All right, and in it actually is going to shed some light even on the first problem, how we solve it, as I mentioned earlier. All right, well, let's look at some of the applications of Legendre Symbol. And as you recall, in chapter 3, we have shown there are infinitely many primes of the form 4k plus 3. All right. Now I'm going to show a similar result, that there are infinitely many primes of the form 4k plus 1. And we're going to see this actually proof is nicer and more straightforward using the quadratic reciprocity. Using Legendre symbol. All right, so this is theorem 9.3. So there are infinitely many primes of the form 4k plus 1. And there are several proofs for these kind of problems or questions. And usually the proof is by contradiction. So let's assume that there are only a finite number of primes of the form 4k plus 1. Let's say, or call them P1, P2, up to P sub r. Then we're going to consider an integer n, which is equal to P1, P2, up to P sub r square plus 1. It's not very hard to see that this one has actually the form. We don't need this, but it has this form, the same form. 4k plus 1. All right, where the k is actually the square of the product of these primes. All right? Now, so with this, then we can say that, first of all, notice that n is clearly is odd. And this implies that n has either it is actually itself is a prime or has an odd prime factor. Let's say P. All right? So this implies that P divides n, and this is equivalent to saying that n is congruent to 0 mod P. Now let's express this congruence relation in terms of what n is actually is equal to. So this is equivalent to this congruence relation, n, which is equal to P1, P2 up to P sub r squared, 1 congruent to 0 mod P. Or this is also equivalent to saying that 2 P1, P2 up to P sub r squared is congruent to negative 1 mod P. And this in itself implies x squared congruent to negative 1 has a solution. Mod P has a solution, which is x equal to P1, P2 up to P sub r, which make the Legendre symbol so this implies that the negative 1 by P is equal positive 1. But we have shown that so this is theorem 9.2. This is the last part of F, that P must be of the form for K plus 1. All right, so this in itself means, therefore, P must equal one of the primes, okay? Pi for some I from 1 to up. Well, let's say I put some divisibility relations. What does this mean? So this means that we have P which is equal P sub I divides N, and we have this N, remember, is equal to P1 up to P sub R squared plus 1. And we have, of course, P sub I divides the product of all of these or their square. And these together, linear combination of these, familiar with this, means it's going to be this one minus that, okay? Plus 1 minus 2P1 up to PR squared, and all of this is equal to 1, and this is, of course, a contradiction. P sub I divides, so we have P sub I divides 1 is equal to. All right, so all the arguments are correct except, our assumption that actually there are finitely many of these primes. All right, here's another theorem that tells us also, among other things, that the number of quadratic residues for a prime and the number of quadratic non-residues are the same. They split in half. Okay, so this is a theorem. Don't think this is not in the book, but this is so simple to actually prove and take advantage of it. Is this. Again, if P is an odd prime, then and A, an integer, relatively prime, to B, then the sum A equal, actually, not really, no, I'm sorry, okay, this is it, okay? Not this, okay? I'm wrong, okay? If this is a prime, then we're just going to add up, actually, A equal 1 to P minus 1 of these, A by P. This equal to 0. Now, hence, because as I say, this implies, hence there are P minus 1 over 2 quadratic residues of P, and same number, P minus 1 over 2 quadratic non-residues of P. Let me actually prove this, because this is a simple conclusion once we prove this summation is equal to 0. We know that A by P, this one is equal plus minus 1, all right? For all these A's between 1 and P minus 1. So if their sum is equal to 0, then half of them is 1s and the other half is negative 1, okay? Since the sum is equal to 0, then half of the summands, they have A over P, are positive 1, and the other half is negative 1. So they can add up, because these are only the values they have, all right? And but half of the summands is P minus 1 over 2. Because we have P minus 1 integers between 1 and P minus 1, so half of them is that. And this actually takes care of the number of quadratic residues and non-residues. All right, so this leaves us with proving the summation is equal to 0. All right, I don't know if we're going to have enough time to prove actually Gauss's lemma, so maybe I need to leave it for some other time. All right, here's the proof. You're going to let R be a primitive root of P. Remember that every prime has a primitive root, so we're in a good shape in here. Then, kind of this argument we've seen before, R squared up to R phi of P, which is P minus 1, forms a reduced residue system of P. So this implies again these integers are R squared up to R P minus 1 are congruent to one, 2, up to P minus 1 in some order. And this in itself implies that for every A between 1 and P minus 1, there exists a unique K, where K is again a unique exponent actually, K. This is going to be exponent between, again, 1 and P minus 1, such that A is congruent to R to the K mod P. All right, so this is because of the reduced residue system, so it will be congruent to each one of these in some order. All right? Now we have by theorem 9.2, so since these are congruent to each other, by theorem 9.2, actually the first property implies that the Legendre symbol A by P is the same as R to the K by P. So they have the same value. All right, now let's look at the Euler criterion with also this one. Tell us. So by Euler criterion, we have R to the K by P is congruent R to the K to the power P minus 1, which is phi of P, mod P. All right? Actually, R to the K over 2. All right? All right, which we can write also as R P minus 1 to the power of K. All right, so this is one thing. Another thing now, we need to use the fact that R also is a primitive root to have another congruence, since R is a primitive root of P. The order of R mod P is equal phi of P is equal to P minus 1, and this gives us this congruence. R to the power P minus 1 is congruent to 1 mod P. All right. Now, let's go in, see, this one implies also P divides R to the power P minus 1 minus 1. All right? And P minus 1 is even. Then we can factor R to the P minus 1 to R P minus 1 over 2 minus 1, then R to the power P minus 1 over 2 plus 1. Okay, now let's write this divisibility using this factoring in here, all right? So we have P divides so we have P divides RP minus 1, which is the same as RP minus 1 over 2 minus 1, and then RP minus 1, 2 plus 1. Well, this implies again, P divides either this or P divides the other factor. Well, the third factor cannot, this is not possible because the order, all right, of R is P minus 1. There is no smaller exponent that actually make this divisible. Okay, so let me write it down. All right. This is equivalent to saying that Rp minus 1 over 2 is equivalent to 1 mod P. But this contradicts that the order of R is actually equal to P minus 1. And remember that this one is actually larger than P minus 1 over 2. We cannot have an exponent smaller than P minus 1. So we left with this. So therefore, we have P divides R to the P minus 1 over 2 plus 1. And again, in terms of congruence, this means that R to the power P minus 1 over 2 is congruent to negative 1 mod P. All right. Now, let's raise both of these to the, actually, we go in here and write what R to the K. Let's go back to this. P. Remember, we have shown that this one is actually equal the same as A to the P to start with. And this is congruent to R to P minus 1 over 2 to the K. But now R to the power P minus 1 over 2 is congruent to negative 1 to the K. Mod P. All right. But let's look at the two sides of this congruence, this one and this one. Each one of these is going to be equal plus or minus 1. So we have a congruence relation here. We're going to turn it into equality. But A over P is equal plus minus 1 for every A between 1 and P minus 1. And the same thing with negative 1 to the K. Again, for every K for the same values. P minus 1. Then they're not equal to each other. This implies that A by P must equal to minus 1 to the K. Because if they are not, Charlie, we did this before, this does not equal to this. This means when one side is going to be positive 1, and then the other one is minus 1. They are congruent. We know that they are congruent to each other. Mod P. So this is the only way they cannot be equal to each other. They give us two different signs, 1 and negative 1. But again, this implies that P divides 2, which is again a contradiction. So in other words, this congruence turns into actually equality. Now let's look at the sum of the Legendre symbol is equivalent to, so therefore, the sum of A by P and A equal 1 to P minus 1 is the same as K equal 1 to P minus 1 minus 1 to the K. And we know that half the integers from 1 to p minus 1 are even, and then the other half is odd, and this gives me 0. That's all. Okay? All right. A corollary to this, and I'm going to be stopping right here, unfortunately, unable to get to Gauss's lemma. So we're going to put this in the second part of this section. So here's the corollary. The quadratic residues of an odd prime are congruent to P, or congruent mod P to the even powers of a primitive root of R primitive root R of P, let's say R of P, and the quadratic non-residues are congruent to mod P to the odd powers. For actually, this follows from the proof itself. In the proof of the theorem, remember we have A by P is equal R to the K of P. And this is equal -1 to the K. That's what we have shown. All right, the Legendre symbol for any, this is true for any. And this implies that A by B is going to equal 1 if K is even. So the exponent of R is going to be even, and going to be -1 if K is odd. All right. All right, and this take care of it. All right. Gonna actually stop right here. As I said, in the next lecture, it's going to be very, very important because we're going to give two versions of Gauss's lemma that will be practical tools of evaluating Legendre Symbol. All right, a simple calculation. Well, some calculation simpler than actually doing the power residues, exponents, which is using Euler's criterion. Okay, because as I said, for large primes, you're going to find it is not actually practical. It will be computationally, hard. All right, so I'm going to stop right here.